Hello everyone again and welcome to my channel. On our previous video we looked at the 3x3 sigmatropic reactions, and most of them either contains oxygen or some of them contains carbon. Now in here we're going to try something quite different, which is using another type of atom, which is now nitrogen. Now nitrogen can be in the form of an amine, amide, imidine and imine, and we're going to see how we'll be able to play around with those in this particular reaction in here to actually perform a 3x3 sigmatropic reaction. So in here we have this phenylhydrazine, and we're going to transform this to a phenylhydrazone, and we're going to see how this is actually done in an acidic state first before we actually proceed with this in our way to actually try to perform a 3x3 sigmatropic reaction. So the mechanism behind this is as follows. In here we have this particular compound. We're going to focus more on this particular segment. Now this actually performs a specific nucleophilic attack on this carbonyl group here, and what we have in this case is the formation of a positive charge on the nitrogen, which is in this particular point here, and then our hydrogens are present here and there, and the other side we do have this tertiary carbon with the oxygen which has a hydrogen in it. Take note that the hydrogen is present here because in here it's been activated by this particular acid, which I forgot to start off with. So by that way you can actually form this hydroxide functional group here. And now what happens next is that once you pick up a proton from an acid, what we have is water present in the system, and what we do in this case is that this water comes in and actually deprotonates this particular section here, and then this becomes a neutral species, and what we have as a result of this is the formation of this nitrogen-nitrogen bond right here. Now that this water actually forms an acid, the acid comes around here, and the hydroxide at some point comes in and actually picks up a proton on this particular acid here, and what happens next is that you're thereby generating a good living group, and then the nitrogen with its lone pair then forms a double bond with this carbon, thereby cleaving this bond off here to produce water and leaving our other segment of our compound in our way to generate a neutral species. Don't forget that since water is being removed here, it comes back and actually deprotonates this particular species here, and what we have is the reformation of our double bond, which is then of our lone pair on this nitrogen, and that results in now the formation of this particular species, which is an imine over here. Next step is that this imine over here is in equilibrium with an amine. So let me write it down because the two words can be kind of misleading to pronounce. And take note that this ring do have hydrogens present in here. Now what happens in this case is that under acidic conditions there is an equilibrium that goes between this particular imine over here and enamine over here. So how is this done? What happens in here is that this acid first comes in, and what happens is that this nitrogen that has a lone pair picks up a proton here by protonation, and what we have is a particular intermediate where we have a nitrogen attached to this hydrogen with a positive charge, and then we have water being formed. And what happens next is that water comes in and picks up a proton by deprotonation, and then this hydrogen leaves, and this particular bond here becomes a double bond on here between this carbon and that carbon, and then this actually forms a lone pair on this nitrogen, therefore resulting in the formation of an enamine Now the question you are going to ask me is, why am I doing this? Why? Now the reason why I'm doing this is that I want my enamine to be able to perform a 3x3 sigmatropic rearrangement, because the sigma bond that will be broken between this nitrogen here is actually weak, and this weak bond will actually further push the reaction towards the 3x3 sigmatropic reaction and result in our product, which is unstable. So in this particular case, we're going to have a 3x3 sigmatropic reaction due to the weak sigma nitrogen bond, and this is actually shown in here, where we have this particular part where this is our 3 3 2 2 1 1 1 1 sigma bond broken, 3 3 sigma bond being formed. So this, that, and this. So what happens in this case is that we actually arrive at this particular product where it's actually unstable. And why is it unstable? I will show you in here, and you'll understand the reason why I'm saying that it is unstable and it needs to be stabilized. So why is this unstable? Now the reason why it's unstable is because we've lost aromaticity in this particular ring, and to be able to restore the aromaticity, we need to be able to actually somehow deprotonate this particular proton here. So what happens here is that the water comes in and deprotonates this, and then we reform our double bond in this particular region. And then what happens next is that this then picks up a proton from the acid that was being formed in this particular step over there. So what happens as a result is the formation of this particular compound, where we restore our aromaticity, and we have this there. So what happens next is that we need to be able to then form our bond in here between this particular nitrogen lone pair, because it's at close proximity with this particular carbon in here. So this particular imine will perform a nucleophilic attack. Just imagine this to be oxygen, but it's not oxygen. So imagine nitrogen being or performing a nucleophilic, an amine performing a nucleophilic attack on a carbonyl, but not in this case, it's not a carbonyl. And then this particular double bond here becomes a form of a base that picks up a proton from this compound, and what we have as a result is the formation of our 5-membered ring within this aromatic ring here, and a 6-membered ring over at this particular region. So this is our 5-membered ring, this is a hydrogen, not to forget, and this is our 6-membered ring here with a nitrogen attached to 2 over there. So this is it over here. Why did I do this? It's meant to be 1 hydrogen in here. I made a mistake, sorry. It's meant to be only 1 hydrogen, so it will become 2 in here. So continuing from this particular step, what we have next is that once we form this is actually a good base that actually attacks or gets protonated again by a particular proton, because take note that this is actually done in an acidic environment. So we have protons around that will actually come in, and with the presence of we understanding the pKa's, then this reaction will continue until it can actually become a stabilized form. So this actually picks up a proton here, and then what happens next is that we form this particular intermediate. So what we'll see here is that since this is being formed, we do have an ammonium here at some point. So in order for this to become ammonia, this is actually known to be a good leaving group, and that particular, in this particular case, this lone pair forms a double bond here, and this bond actually cleaves and relays ammonia in this particular case. And what we have as a result is the formation of our pre-product, where we have a 6-membered ring, benzene ring, attached to or fused with our 5-membered ring with a nitrogen attached to hydrogen with a positive charge on our nitrogen, and we have a proton here, and we have our 6-membered ring over there fused to it. Now what happens next is that, hey, since ammonia is actually released here, and take note that we have, in this case, water being released here, we can either use ammonia or water in this case to actually deprotonate this particular region. In this case, we can either use water or ammonia, but I'd rather use water just to reform our acid. And what we have is the picking up of a proton here, and this actually forms a double bond here, and this reforms our lone pair on this particular nitrogen. And what happens as a result of that is the formation of this particular compound, which is an aromatic indole. So that's about it for this particular reaction, and I think this is where it's going to stop at. It won't proceed further because in here we formed a stabilized compound. We've restored the aromatic ring. We'll be able to actually form a strong bond in here in such a way that there's no bond that will be cleaved in here. And that's about it for this particular video. The most important thing is we're recognizing that the key step in here is the 3x3 sigmatropic reaction in here that actually pushes it with a sigma bond that is really weak, which is a nitrogen bond in here, and then other things kind of plays a role in terms of protonation and deprotonation, and then leading to our final product in here. So that's about it for this particular video. Truly appreciate it. Please hit the comment down below, let me hear your thoughts, and see you all on my next video. Have a good day. Peace, love you all, and be smart.